Hi, in this video, we will be learning about page replacement algorithms in operating systems. Page replacement algorithms are very much essential in virtual memory management. Before getting into the algorithms, let me refresh some of the important concepts in virtual memory management. Paging. What is paging? Paging is a memory management scheme that permits the physical address space of a process to be non-contiguous. The basic idea of paging originated in order to avoid external fragmentation. What is involved in paging? The basic method for implementing paging involves breaking physical memory into fixed size blocks called frames and breaking logical memory of the same size called pages. That is, the logical address space is that of a program and the main address space or the physical address space is that of the main memory. And these are divided into chunks called as blocks of equal size. When you are referencing the main memory, these blocks are called as frames, and when you are referencing to the logical address space, these are called as pages. Demand paging. What is demand paging? When we want to load a program into memory, instead of loading the entire program, we can load pages only as they are needed or as they are demanded. That is, only when we require a page, we call the page from the disk into the memory, and the whole program need not be present in the main memory during the execution time. Let us get into the page replacement algorithms. So, what are our motives in coming up with a good page replacement algorithm? We want lowest page fault rate. So what is a page fault? A page fault is a trap to the software raised by the hardware when a program accesses a page that is mapped in the virtual address space but not loaded in the physical memory. In simple words, suppose a page is required for a program to execute and it points to that particular page in the main memory, but that particular required page is not present in the main memory, but it is present in the logical address space. So this causes the hardware to raise an exception or a fault, and this terminology is called as page fault. And how shall we evaluate how shall we evaluate page replacement algorithms? We'll be evaluating the replacement algorithms based on the value of page fault. Let us look at some of the relationships between page faults and the number of frames used. The graph mentioned here mentions about the relationship between the page faults and the number of frames, and this gives a condition that the page fault is inversely proportional to the frames. So this graph clearly suggests that as the page fault decreases, the number of frames increases, or the other better way of saying this is that as the frame size increases, the number of page faults decreases. The FIFO policy, or the first page replacement algorithm. The FIFO policy treats whatever the incoming page in a first come first served order. If a page request has come and there is no space for the page to be accommodated within the frame, then some page has to be replaced. So the policy adopted by FIFO is first in, first out. So whichever page came first will be replaced by the newly arriving page. Let us look at a simple example for that. Now, this is the given reference string which we'll be using in order to demonstrate the FIFO page replacement algorithm. The request for 7 comes. Now, when 7 comes, 7 is not present within the frames, so it's a page fault, and 7 will be put into an empty slot. Now 0 comes. When 0 is not present, it's a page fault. and 0 will be filled into an empty slot. No replacement required, as there is no competency or the competition for getting into the frame, since there are empty spaces. Now 1 comes. When 1 comes, when 1 undergoes a page fault, and it will be put into an empty slot available. Now when 2 comes, there is no empty slot available, so some page within 701 has to be replaced with 2. And according to FIFO policy, whichever page came first is going to be replaced by 2, that is 7. And you can clearly see here that 7 is the one which came before 0 and 1, so 7 will be replaced, and the new frame is 201. Even 2 accounts for the page fault. Now when 0 comes, 0 is already present, so this does not account for a page fault. Now when 3 comes, again 3 is not present, page fault, and 3 has to be put in place of one of these 3 frames. And so which frame is the one that needs to be replaced? According to FIFO policy, 0 should go out, so 0 is replaced by 3, so the new frame is 3, 2, 3, 1. Now 0 comes, 0 is not present, page fault. Now 1 should be replaced according to FIFO policy, so 1 goes off and 1 is replaced by 0. Now 4 comes. When 4 comes, again 4 is not present, 4 has to be replaced, and the next element which will be eliminated is 2 according to FIFO policy. Now 430, and when 2 comes, 3 will be taken out and 2 will be put in. When 3 comes, 0 will be taken out and 3 will be put in, and when 0 comes, 4 will be taken out and 0 will be put in, and when 3 comes, it's already present, 2 comes, it's already present, and 1 comes, again replacement, 2 is replaced according to FIFO policy. And similarly, and by the time the final request comes, this will be the final state of the frames. Now from the example mentioned above, we saw that for the frame size equal to 3, the number of page faults we got was 9. That included 1, 2, 3, 4, 1, 2, 4, 3, 5 requests, wherever in the order. Wherever we found the page fault, we have circled it in the video. Now suppose the page fault, suppose we use the frame of size 4. We see that the number of page faults occurring for the frame size is 10. But for the frame size 3, the number of page faults occurring is 9. What's happening? If you see the graph before the algorithm, the graph clearly suggested that the frame size is inversely proportional to the page fault. But here, if we increase the frame size from 3 to 4, the page fault is also increasing. This special anomaly, which was found out during some research work, is called as Melodi's anomaly. This is applicable only to FIFO algorithm, and from this graph you can see that for a frame size of 3, the page fault occurs at 9, and for 4 it is at 10. This is a particular anomaly which does not follow the graph consistently which we showed before. The optimal page replacement. In the optimal page replacement policy, the page which has to be replaced is chosen in such a way that it will not be used for the longest period of time. That is, if suppose a page has to be replaced, then its request does not occur in the near future. Or in simple words, we can treat that with a page to find a page which occurs at the last to the right of the request arriving. Now, let us consider the same reference string for checking about optimal page replacement algorithm. Now 7 comes, page fault, 7 is put into an empty slot. As usual, 0 comes, page fault is put into empty slot, 1 comes, 1 is put into empty slot. Now when 2 comes, there is no empty slot available, so some frame has to be replaced. Which frame is it? According to optimal page replacement algorithm, you need to check for the page which does not occur in the near future, or which is the farthest towards right when among the three pages. If you look at the pages 701, 0 occurs here, 1 occurs here, and 7 is the one which is very much far. So 7 is the one which needs to be replaced according to the optimal page replacement algorithm, and it is in the place of 7, 2 is put in. Now 0 comes, 0 is already present. Now 3 comes. When 3 comes, again a page fault. Sorry, I'm just on the page fault for 2 here. Now when 3 comes, again somehow the other page present here needs to be replaced. Which page is it going to be? Let us see. 201. 0 occurs here, 2 occurs here, and 1 is the one which is occurring at the farthest. So according to optimal replacement algorithm, 1 is the one which should be taken out, and so 3 comes in here. Now 0 comes, 0 is already present. 4 comes, again replacement should happen. And according to page replacement algorithm, out of 203, 2 occurs here, 3 occurs here, and 0 is the one which is the farthest. So 0 needs to be replaced, and 4 comes in. Now 2 comes, 2 is already present, 3 comes, 3 is already present, 0 comes, the replacement happens, and similarly the replacement algorithm continues, and this will be the final state obtained after this algorithm. And if you use the same algorithm for a frame size of 4, we can see that 6 page faults occur, and you can confirm this by using the same example. So the LRU policy, or the least recently used, this is the third page replacement algorithm and the final one which we will be discussing today. According to the least recently used policy, the algorithm replaces the page that has not been referenced for the longest time. And by the principle of locality, this should be the page least likely to be referenced in the near future. The LRU page replacement algorithm. Let us look at an example for this algorithm. Now, again we'll take the same reference string which we considered for FIFO as well as optimal. 7 comes, 7 is put in, 0 comes, 0 is put in, 1 comes, 1 is put in. Now when 2 comes, we are going to check for the least recently used page. Among 7, 0, 1, the page which is least recently used is 7. And how do you find out? From the given request, check towards your left whichever occurs the last, that is the least recently used one. 701, 7 is the one which is occurring, which is the least recently used page, so 7 is taken out and 2 comes in. This is the new one. Now 0 comes, 0 is already present. 3 comes. Now out of 201, which is the least recently used, now we are at 3, we go to the left, 0, 2, 1. So 1 is the one which is least recently used, so we take out 1 and replace it with 3. Now 0 comes, 0 is already present. 4 comes. Now we need a replacement. Which page are we going to replace? Out of 203, now we are at 4, 0 is present, 3 is present, and 2 is the one which is occurring late, which is the least recently used, not late, sorry. Now 2 is replaced and 4 comes in, and in a similar fashion the whole procedure continues until we end up with this as the final state. Now for the comparison purposes, let us compare the performance of optimal page replacement algorithm with the least recently used page replacement algorithm for the same page address string or the reference string. Now if you see with the optimal page replacement algorithm, we get the page fault as 3, which here we get the page fault as 4 for the given same frame size. So from this we can say that the optimal is better than LRU in most situations. This is a second comparison between LRU, least recently used, and FIFO. Now, we saw that LRU is worse than optimal in most of the situations. And again, for the same page at a stream, we check for the performance of LRU and FIFO. And if you look at this, for LRU it is 4, but for FIFO it is 6. 6 is very much greater than 4 and very much greater than 3 in terms of page fault. So FIFO is the one which is less efficient among the 3 algorithms which we discussed today. The LRU policy can also be implemented in many different ways. If we can do it like we can tag each page with the time at the each memory reference, and the LRU page is the one with the smallest time value, and this is just another implementation. But the drawback with this implementation is that it would require expensive hardware and a great deal of overhead, because we need to take the time at each memory reference. So consequently, very few computer systems provide sufficient hardware support for the LRU replacement policy. And there are other implementations which can be performed using stack, and wherein we can keep a stack of page numbers in a doubly linked form, and the page reference to move to the top, and requires 6 pointers to be changed. These are all the overheads which we need to use, and we need not search for replacement as it will be directly present on the top. That is the one which is least recently used. And here's a page which can give us some clear indication into the implementation using stack. So that's it. Thank you. Hope you learned something.